It is 101. So, um, yes. Our next speaker is Aled Walker from Trinity College, Cambridge. Please.
Well, thank you very much, Mel, for the invitation to speak at this astonishingly large workshop. Incredible organization to have 106 speakers in who knows how many time zones giving Zoom talks. I should start by saying, of course, that everything I'm going to speak about today is joint work with Andrew Granville and George Shaken. And the paper that I'm talking about, the main results from, we put that on the archive last week. If you want to see more details about the proofs or a bit more of an introduction to this general area, then you can just go and Google. The title is the same as the title of my talk, Effective Results on the Size and Structure of Sumsets. Okay, the setup is going to be extremely general, at least initially. We're going to take an abelian group G and some finite set contained in G. And just for this talk, just to simplify some of the statements, I'll assume that 0 is in A, 0 being the identity of the group G. We can just translate A so that that's the case. And just for simplicity, we'll assume that A generates this group G that it's contained. Okay, so the very vague initial question is this: what can be said about the size and structure of the iterated sumset NA? Well, not when n is 2, 3, or any other fixed bounded quantity, which is, of course, what we study perhaps most of the time in additive combinatorics, but rather when n is extremely large. Okay, is there anything sensible you can say? And if so, how do you say it? Okay, well, of course, if G is finite, this question is completely stupid, because you can just go away and generate the whole finite group using A once n is large enough. And this has the following, this is such a strange thing to be writing, but you'll see why I write it later on, that of course, when n is large enough, the function that sends n to the size of the sumset NA is eventually constant, because you've just gone away and generated the whole group. And in the absolutely worst possible case, when A has 2 elements, that takes, well, the size of the group G to occur, but once you have more, n is at least the size of the group G, then you generated everything, and there's nothing left interesting to say about the sumset. All right, so the finite case is completely stupid, but already once the ambient group is infinite, is Z, then there's something slightly non-trivial that happens. So here's an example when A is just 3 element set, 0, 3, and 5. And I've written for you here the iterated sumsets 2A, 3A, 4A, and so on. And one notices that while there's some slight irregularity at the beginning, one then gets a full interval up to some point near the end, and then you miss a few things at the end. And one can just prove by induction that that's always the case. You get every integer point between 0 and 5n, but you miss 1, 2, 4, and 7 always, and also you miss 5n minus 1 and 5n minus 3. So in this case of 4a, you're missing 19 and you're missing 17. But everything else you get. Okay, so that's some structural description of NA when n is large. And of course, if n is large enough so that these 2 exceptional sets are disjoint, then the size of NA will grow linearly with n. Okay, so this happens once n is at least 3. These 2 sets are disjoint, and therefore the size of NA is always 5n minus 5 for all n going forward. Okay, but this doesn't hold for n equals 2 or n equals 1, because these exceptional sets intersect at that point. Okay, so what's going on with the set 1, 2, 4, 7? Well, it's not terribly deep. These are the elements that can't be represented as any non-negative integer sum of elements of the set A, namely 3 and 5. Okay, so you can't represent 4 no matter how many copies of 3 and 5 you pick, so therefore you're never going to represent it by at most n copies of 3 and 5. So that's why you never get 1, 2, 4, or 7. Okay, these type of sets will come up a lot in the talk, so I'll give them some notation, E of A, and I'll call them the exceptional set for A. These are the things that cannot be represented by any non-negative integer combinations of A. Now, okay, when G is Z, we're dealing with numerical semigroups here, and so this has its own name in the numerical semigroup literature. This is called the set of gaps in the numerical semigroup. Okay, I'm heading towards z to the d, which is really where we've proved some new results. And I feel that this name, an exceptional set, is a bit more descriptive of what's going on there. Anyway, so that's what's going on with 1, 2, 4, 7, but why don't we get this set 5n minus 1 or 5n minus 3? Okay, so here I've just repeated the set A and the structure. The reason is because there's a reciprocity, which I'll state in slightly more generality. Let's say that the minimum element of A is 0 and the maximum element is B. Okay, in this case it's fine. Then this is the reciprocity I mean, that if X is in the sumset NA, well, that's if and only if Bn minus X is in the sumset NB minus A. Okay, this is a completely trivial one-line observation, and here's the one line. Okay, but this means that the exceptional set of B minus A will crop up as an obstruction to NA equaling the entirety of this interval from 0 to Bn. Okay, so in this example, B minus A is the set 0, 2, 5, and the exceptional set for 0, 2, 5 is 1, 3, and that's why you get 5n minus 1 and 5n minus 3 as exceptional elements. Okay, so for all n at least 1, the sumset NA is contained in this set on the right, which looks a bit horrible, but I hope I've described enough of what's going on here. It's integer points contained in this dilated interval, but I miss something at the beginning coming from the exceptional elements of A, and I miss something at the end coming from the exceptional elements of B minus A, suitably translated. Okay, but equality in this inclusion doesn't always hold, and in fact there are examples as soon as the size of A is at least 4. Okay, here's one example. Set of A is just 0, 1, B minus 1, B for any B you care to mention. Say B is 10, 0, 1, 9, 10. There are no exceptional sets. Every non-negative integer can be represented as the sum of elements of A. However, you need n to be pretty large in order to represent everything in the interval 0 to Bn. Okay, so look here, if n is at most B minus 3, B minus 2 is contained in the right-hand side, but not in the left-hand side. You know, it takes a while to generate B minus 2 by repeatedly adding elements of A. Okay, this is just all to say that there's something going on here, that equality in this expression is not always bound to hold. Right, but it was one of Mel's early results in the early 70s to say that if n is large enough, then equality does hold. And in fact, he did this effectively. So we have 0 being the min element, B being the max element. Then there is some explicit threshold, I'll call this the structural threshold of A, n structure, such that equality holds in this structural decomposition for all large enough n that are at least this threshold. And Mel gave a bound on the structure constant, B squared times the size of A minus 1. Okay, now just in case anyone is going to crop up, remember I'm assuming that A generates G all the time. So I'm assuming that the GCD of all the elements of A is 1, just to remove that kind of trivial technicality. Okay, so this bound has been decreased over the years, and the record, I think, is still due to Andrew and myself from last year. And this is tight in infinitely many examples we showed. Okay, so that's structure. What about size? Well, the same thing holds. If n is large enough so that structure holds, this structure holds, and the two exceptional sets are disjoint, then we're going to be linear in size. The size of the sumset will grow linearly with n. So this is what's going on here. The size of the sumset is bn plus 1, that's all the integer points in this range, minus the size of the two exceptional sets. Okay, and that certainly happens once n is large enough for structure to hold and for the two exceptional sets to be disjoint. Okay, and we have the results of Andrew and myself to bound the structure constant, and some cheap results can be used just to upper bound the exceptional sets. And you can show that b minus 1 is enough. If n is at least b minus 1, then you're going to grow linearly in size above that threshold. Okay, so this is all to say that the dimension 1 case is relatively well understood by now, which is in contrast to the D2 or above case. What is known? Well, there is this celebrated result of Khovansky from the early 90s, which says something I find still really remarkable. I was very surprised when I first came across this result. It says that if I take a finite subset of z to the d, then there is some fixed polynomial, p of a, well, it depends, with rational coefficients and degree at most d, and some threshold, I'll call this for this talk the Khovansky threshold, such that the size of the sumset is equal to the polynomial evaluated at n for all n that's at least the Khovansky threshold. Okay, and I'm not talking about just polynomial growth in general. It's quite easy to convince yourself that the sumsets grow roughly polynomially, but it's a polynomial on the nose, at least when n is large enough. Okay, so as I said, I still find this result somewhat surprising. But what do we know about this Khovansky threshold? And the answer was not much. Well, for d is 1, it's all fine. So as I said before, the Khovansky threshold is at most b minus 1 for d. Well, what about Khovansky's proof? Well, it was a very ingenious proof. It was an algebraic proof. He related the sizes of these sumsets to the dimensions of certain components in a graded module. And there's this old result of Hilbert that says that eventually the dimensions of these components grow polynomially. But, well, you can give some effective bound on this if you know the generators for the module, but we don't know the generators here, so that's as hard as the original problem to understand what the generators are. So Khovansky's proof gives an ineffective bound on the Khovansky threshold. Now, 10 years later, Nathanson and Ruja gave a very nice combinatorial proof of the same theorem, but again, it was ineffective, and I can explain more precisely why this proof is ineffective. It relies on the following fact about subsets of the positive quadrant of z to the d. Okay, what's this fact? It's a lemma, I think, goes back to Dixon. For any subset of the positive quadrant of integer points, there is some finite subset of minimal elements, S min. Minimal in what sense? Well, every element of S lies above and to the right of some element of S min, i.e. that there's some x such that S minus x is a positive coordinate point. Now, I've drawn a picture to show you what this looks like in practice in 2 dimensions. So in 2 dimensions, this blue shaded region is S. The integer points in that region are S. And these red points are S min. They're basically the corners of this set. Now, you can maybe even see just by this picture that there's going to be finitely many of them. Okay, this is in 2 dimensions, it's easy to see what's going on. But also you can see how potentially there could be arbitrarily many of them. Right, so this is a big change from 1 dimension where there's just one minimal element. And so Nathanson and Ruja phrased their Khovansky threshold in terms of these minimal elements for a certain set S, which I'll mention later. But unless you find a way to get a more precise handling on S than just using Dixon's lemma, you're always going to just get some ineffective constant because it's based on an existence result. It's based on an existence of finitely many minimal elements. Okay, well, was anything effective known? Well, there were some results known. Now, I'm not going to talk too much about this slide because there's going to be a talk about it later in this workshop. I believe Michael Curran is going to speak about this result. So I'm not going to double up on that, but just to state the results, you have the convex hull of A, right? That's just the real combinations of the elements of A, so sum to 1. We say that it's a D simplex if there are D plus 1 corners to it. So if in 2 dimensions, if your convex hull is a triangle, in 3 dimensions, if your convex hull is a tetrahedron, and so on. Now, it was observed very cunningly by Curran and Goldmacher that this case is much more tractable than the general case. That if you assume that the convex hull is a D simplex, then you can get a very explicit effective upper bound on the Khovansky threshold. So here it is. And they actually, they did one more special case when the size of A is D plus 2. And so in this case, they got, in fact, bang on the nose. They explicitly calculated the size of the sumset for all n. And here is what the Khovansky threshold is. Okay, here are these two theorems again. This is the same as on the previous slide. I do want to just relate them to things I've talked about earlier. So earlier we had this example, 035, and we noted that it was linear growth once n was 3 or more. And that's this threshold from the second theorem of Curran and Goldmacher. Because the volume of the convex hull, well, that's just the length between 0 and 5. Okay, so you plug that in and you get 3 from this threshold. Now, this subtlety that Curran and Goldmacher observed, that the simplex case is easier than the general case, is more tractable, is something you only notice when you go to higher dimensions. Because in one dimension, you don't see it, because everything has a simplex for its convex hull. Because a one simplex is just an interval. And so in one dimensions, every set has one simplex as its convex hull. That's something to note. And just finally, Curran and Goldmacher didn't quite manage to match in general the bound that Andrew and I got for one dimension. And the issue with all of this is this d plus 1 factorial term. We kind of think it should be d factorial, and in one dimensions we can prove this, more or less. But in higher dimensions, we're kind of stuck at d plus 1 factorial, and this persists into the work that I'm talking about today, the new results to come in subsequent slides. So if anyone's looking for a new problem to think about, getting this threshold down so that this factor is more like d factorial rather than d plus 1 factorial, I think is a very interesting thing to be working on. All right, so what's new? We have an effective Khovansky threshold in all cases. Okay, so we're going to phrase this threshold in terms of this thing we call the width of A. This is just some crude measure of the complexity of A. That's translation invariant, which we thought was a good notion because some sets don't depend on translation. Okay, and here's the bound. It's not the prettiest thing in the world, but nor is it the worst bound ever seen. That the Khovansky threshold is at most, well, this function, 2 times the size of A times the width of A, all to the power d plus 4 to the size of A. Now, we don't claim this is a tight bound, although it's not so far from lower bound examples, which you can show that the width of A to the d is at least necessary. But as I said, this is the first bound that's known universally over all sets A. I have a slide right at the end of the talk where I give a few more details about the proof, but the one-sentence summary is that we do follow what Nathanson and Ruja did, but we have to completely bypass Dixon's lemma, and we rephrase the study of these minimal elements in terms of quantitative linear algebra. We construct a quantitative linear algebra argument for analyzing and bounding these minimal elements, and then we can put them into the Nathanson-Ruja scheme without too much alteration. We also thought about the simplex case, and we managed to, by very different methods, get a slight improvement to Curran and Goldmacher. It's not much. Note that we still have this d plus 1 factorial factor here, so we haven't got d factorial, but we've managed to get a saving that gets bigger the larger A is. So this is a slight extra saving than what Curran and Goldmacher were able to get. Okay, so that's our new results for the Khovansky question. But what about effective structure? That's what I started with, right? Talking about the structural properties of NA when n was large. Okay, so in order to even state this result in higher dimensions, I need to tell you what an exceptional set means in higher dimensions. And this will just be a very small amount of notation. Here it is. So for a given subset A of Z to the D, we'll let C of A denote the cone generated by A. So these are all the non-negative real combinations of elements of A. On the next slide, I have an explicit example with a picture to make this easy to understand, I hope. And P of A, I'll let that denote the sum of all non-negative integer combinations of elements of A. And the exceptional set, E of A, is what's left over. So this is everything that could potentially be sums of non-negative integer combinations of A, but isn't. Okay, this is everything with positive real coordinates that's an integer, but nonetheless is not represented by positive integer combinations of A. So this is the right notion of the exceptional set in this higher dimensional setup. And here's an example. Okay, so this is just a 4-element subset in 2 dimensions. It's got the origin, 2, 0, 0, 3, and 1, 1, and I've colored this in red. Okay, so these are the red points down here. The cone in this case is the entire positive real quadrant. Right, that's what you get by combining positive real combinations of these elements. These black points are the rest of P of A. These are things that are non-negative combinations of elements of A. And what's left, those are the blue points. That's the exceptional elements. So if you look at this point, this is 3, 2 here. There's no way of writing 3, 2 as a non-negative integer combination of elements of A. Okay, so you notice already that these exceptional points hug the boundary of the cone a bit. No, there are blue points here, but no blue points once you get far enough into the interior of the cone. That turns out to be a general phenomenon that, in fact, Khovansky proved back in the 90s. Anyway, so that's just an example of this notation, and just here is the sumsets of A growing. Okay, if anyone was concerned that there were loads of slides in this talk, we've just done 5 slides in 5 seconds. So you see that we're contained in the dilation of the convex hull of A, but there are holes, right? There are holes given by the exceptional elements. And we want to know how high you got to go so that the only exceptional things you don't hit are ones you could never possibly hit because they are exceptional elements. And that's what we show. We show this effective structure, which is a straight generalization of the one-dimensional case, which I just remind you of here. This was, in fact, what Nathanson proved back in the 70s. And so here's the generalization. There is some structural threshold for which the sumset NA is everything you could possibly get in the dilation of the convex hull, but you've got to remove the exceptional elements. Okay, and so we prove this with an effective threshold for the structure, which is this. Okay, so again, note this really is the generalization, because in one dimension, the extremal points of the convex hull are just 0 and B, right? The min element and the max element. So that gives us E of A and Bn minus E B minus A. And that's exactly what we have here. We're taking the union over the corners of the convex hull, over the extremal points, and removing these exceptional elements that we would have never had any hope of representing anyway. All right, so the ineffective result was proven by my co-authors last year. But again, using Dixon's lemma. So it's the same source of ineffectivity that came up in the Nathanson-Ruger work. And Cohn and Goldmacher, again, they showed that in the simplex case, where the convex hull is a D-simplex, then you can actually get an effective bound on the structural component. But this is the first time that we've got an effective bound over every finite subset A of Z to the D. Okay, now I do have a small amount of time left, I think, and so I just have 2 slides on the proofs at the most very basic level. So this is about the Khovansky thing, and here I'm reminding you of Dixon's lemma. So we've got this minimal set, S min. How might we control an element in S min? Well, here's a possible approach. Let's take some explicit element of S. Say we can get our hands on something explicit in S, call it S star. Now, this means that there's some coordinate, I, we're in n-dimensional space, some coordinate I, for which the minimal element, the ith coordinate, is smaller than Si star, right? Otherwise, this would have no right to be called a minimal element. No, I could remove it from the set S min without losing any of the structure. So I bounded one coordinate of the thing I wanted to control. That's not bad. I need to bound all the coordinates. How do I do that? Well, I split into fibers. Every possible value of the ith coordinate, K, So this goes from 0 up to Si star. I separate S into various fibers given by fixed values of the ith coordinate. The ith coordinate is equal to k. And this set lives in one dimension less, right? Because I fixed the ith coordinate. So it lives in n-1 dimensions. And then I can rinse and repeat, right? I find an element in Sk that will in turn lead to some coordinate for which I can bound the S-min coordinate at the jth coordinate, say. And then I just keep going. However, of course, to do this, I'm going to need to understand elements of S extremely well, because not only do I need to find elements in S, I need to find elements in S with a fixed first coordinate or with 3 fixed coordinates or 10 fixed coordinates, and so on. But it turns out in the Nathanson-Ruja method, you can do this. So I won't describe that full method, but we interpret it, we show that you can reduce the minimal element calculation to finding certain minimal solutions to this kind of linear algebra problem, where you have some subsets of A, I1 and I2, and you're looking at kind of some generalized additive energy expression where you also require that the weights on both sides are the same. Okay, so I won't go into this side, I have time. But you can, by quantitative linear algebra, find elements in such solution sets. And once you fix coordinates, okay, then you have inhomogeneous linear equations, but you can also quantitatively control those by similar things. So we use the power of this quantitative linear algebra approach to get the effective. Okay, and here's a picture of what's going on, which is in 2 dimensions. You find some solution to your linear equation, and that controls the region where the minimal element can live. And okay, it's not a bounded region, but there's one coordinate or other that is bounded, and that's enough to induct upon by the dimension. Okay, so I see that my time is basically gone, and I think I should stop here. But if anyone's interested in the proof of the structure result, which actually is the hardest proof in the paper, so this takes up almost half the paper doing the structure results, then we have long sketches in the paper. Okay, so thank you very much for your attention, and over to me.
All right. Thank you very much, Aled. Lovely talk. We have roughly 2 or 3 microseconds until the next talk. So I just to make one very quick remark. You know, Khovansky used this Hilbert polynomial, which fits into algebraic geometry and commutative algebra, but it's essentially the same result as Dixon's lemma. And Hilbert's polynomial is a very combinatorial object, and it's not at all different from Dixon's lemma in counting lattice points. So there's a kind of apparent difference in algebraic versus combinatorial, but the Hilbert polynomial is really just another combinatorial device.
So you feel that your proof with Ruja was something just of a reinterpretation of Khovansky's method, just
Well,
going...
it wasn't, not so much that it was a reinterpretation, but it's slightly misleading to say that we didn't need to use the Hilbert polynomial. We used Dixon's lemma, which is more elementary. But
I see.
And in fact, Dixon, I mean, his so-called Dixon's lemma comes up, and actually he was trying to understand perfect numbers, and he independently discovered the Hilbert Null-Stauensatz. I mean, a lot of the classic theorems of Hilbert were done at about the same time as Dixon, and some of them Dixon discovered independently, working on some number theoretical problems. Just curious. Anyway,
thank you very much.
So Aled, you need to
I need to stop
your screen share.